quicker than the texture of space-time can stay aware of it. It'll simply tear, and I'm unnerved by this right now. Our night sky is changing quickly, and in simply a question of many years, if not mere years, it could turn out to be totally unrecognizable. Cosmologists worldwide are sounding the alarm. Experts like deGrasse Tyson have recently confirmed the inevitable explosion of Polaris, and the story behind it is very terrifying. Polaris, known as the North Star, has long been a constant in our night sky, serving as a critical reference point for stargazers, pilots, and astronomers. However, this could soon change, altering our night sky and astronomical measurements forever. Let us delve into the significance of this threat and its implications for us all. Join us as we uncover the narrative of Polaris as it moves toward its end. For a long time, Polaris has guided sailors and astronomers alike, holding a cherished position as a guiding light. Its steadfast presence in the night sky has been essential for navigation. Yet, this stability may soon be disrupted. In September 2012, a research paper presented by the esteemed Royal Astronomical Society cast doubt on the fate of this celestial illuminator. Polaris is on the brink of exploding, potentially disappearing from the night sky forever. Before we examine the consequences of this revelation, let us learn more about Polaris. Also known as the North Star or Pole Star, Polaris is unique due to its proximity to the celestial North Pole. Positioned directly above Earth's North Pole, it appears almost stationary in the northern sky. Found in the constellation Ursa Minor, or the Little Dipper, Polaris shines as a moderately bright yellow-white supergiant star, much larger and brighter than our Sun. Polaris is not a single star but part of a complex triple star system, with Polaris A and Polaris B forming a double pair while Polaris B orbits around them. The interactions among these stars create gravitational forces that shape their orbits and affect their behavior. Any disruptions in these interactions can lead to irregular variations in the star's brightness or pulsation patterns. However, the exact mechanisms behind these interactions remain unclear. Polaris is located approximately 323 light-years from Earth, meaning the light we see from it today began its journey over 3 centuries ago. Therefore, if Polaris were to explode now, we would not witness it for another 300 years. It is even possible that Polaris has already exploded, and we are yet to observe the light from that event. Throughout history, the North Star has held immense cultural, navigational, and symbolic significance. Its stability and fixed position made it an invaluable guide for ancient sailors, steering them across seas and lands. Symbolically, Polaris represented constancy and guidance, remaining steadfast amid the ever-changing night sky. For astronomers, Polaris served as a vital reference point, aiding the study of celestial motions and variable stars. As a Cepheid variable star, its periodic variations in brightness have provided valuable insights into stellar properties and the nature of variable stars. This characteristic also played a crucial role in determining cosmic distances and calibrating instruments. These pulsations follow a predictable pattern, which has been the norm for the star, making it easy for us to anticipate its behavior. However, recently, Polaris has deviated from this regular behavior. This anomaly in its pulsation cycle has puzzled astronomers, leading to a closer examination of this celestial oddity. Instead of its usual predictable pattern, Polaris has started exhibiting erratic cycles of dimming and brightening. Scientists are now raising concerns that the star might be nearing the end of its life. This aligns with behaviors typically observed in stars nearing their demise. The ongoing elongation of Polaris' pulsation period, which was once stable, can be attributed to interactions within its star system. We have observed an annual increase in the pulsation duration of 4.5 seconds, which may seem insignificant but holds significant implications. Some astronomers suggest that gravitational interactions between the Polaris stars could be causing these fluctuations in its atmospheric conditions, directly affecting its pulsation patterns. However, others are more alarmed, believing the star is on the brink of exploding. The similarities between Polaris behavior and that of Betelgeuse, another prominent star in the Orion constellation, are striking. Both stars have displayed puzzling anomalies in their luminosity, raising concerns about potential explosions. Stars in their twilight stages often exhibit such irregularities before reaching the climax of their life cycles. While NASA has expressed heightened concern about Betelgeuse, similar attention has not yet been officially directed toward Polaris. Yet, as a Cepheid star approaches the end of its life cycle, it progresses through various stages, including the main sequence stage, red giant stage, and finally the supernova explosion. Based on Polaris' erratic pulsations, scientists predict it has entered the stages of helium depletion typical of Cepheid stars nearing their end. These anomalies in Polaris behavior align with patterns indicative of Cepheid stars in their twilight stages, yet definitive signs of its impending supernova remain uncertain. Astronomers are continually analyzing these anomalies to determine Polaris' fate. If Polaris were to go supernova, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance could dramatically transform our perception of familiar constellations like the Big Dipper, of which Polaris is a part. Rest assured, Earth would likely be entirely safe even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually dramatic as Betelgeuse's, it could still be visible to the naked eye for an extended period and outshine nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the scientific community and among stargazers worldwide. However, the specific visibility and impact on Earth's atmosphere or surroundings would be less significant compared to a closer supernova event. But what about Polaris itself? What will be its fate after a potential supernova event? Let's clarify one thing. While massive stars typically end their lives with a supernova, this is unlikely to be the case with Polaris. When a massive star goes supernova, a massive explosion occurs within it, marking the final catastrophic stage in its life. This process involves a complete collapse of the core, triggering an intense shockwave that causes the star to explode violently. However, Polaris is not massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transition into a white dwarf. This transformation will not result in a supernova but rather a peaceful end as it evolves into a small, incredibly dense celestial remnant. A white dwarf is the leftover core of a low or medium-mass star that has depleted its nuclear fuel. It is incredibly dense, roughly the size of Earth but as massive as the Sun. Planets similar to what we notice in the star today, contrasting the expected impacts of Polaris, are overflowed with verifiable cosmic explosion events. These events give significant insight into the advancement of stars and their ultimate destinies. Comparing our assumptions and legitimate supernovae, like SN 1054 or SN 1987A, and later events such as SN 2011 Fe or SN 2014 J, provides valuable data for understanding the possible fallout of Polaris burst. SN 1054, for instance, resulted in the formation of the Crab Nebula, a cloud that continues to expand and emit radiation across multiple wavelengths, offering astronomers a rich field of study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, provided insights into the processes of nucleosynthesis and the dynamics of supernova remnants. Analyzing phenomena such as the formation of nebulae, the release of cosmic rays, and variations in luminosity can offer insights into Polaris' unique characteristics. The formation of nebulae, like the Crab Nebula, results from the expulsion of material during a supernova explosion. This material interacts with the surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the cycle of stellar birth and death. Moreover, the release of cosmic rays, high-energy particles accelerated by supernova shockwaves, has implications for astrophysical processes and cosmic radiation environments. To make a definitive comparison, scientists evaluate differences in mass, composition, and velocity of ejected materials between Polaris potential burst and other observed events. This involves studying the light curves, spectra, and remnants of these events and projecting similar characteristics for Polaris expected burst. Assessing whether Polaris burst could lead to the formation of nebulae or distinct elemental distributions enhances our understanding of its potential outcomes. Another crucial area of examination involves evaluating the pulsational variability of stars nearing their end stages, akin to Polaris, against observed supernova progenitors. This comparative analysis can help identify similarities or deviations, providing insights into the burst mechanism. Pulsational variability in stars nearing the end of their lives may indicate internal instabilities or impending catastrophic events, offering clues to the evolutionary processes leading to supernova explosions. Despite detailed observations and extensive analysis, astronomers remain perplexed by the anomalies observed in Polaris behavior. Unraveling the unique conditions driving these irregularities holds the key to advancing our understanding of stellar evolution. Understanding the mechanisms responsible for Polaris erratic pulsations requires interdisciplinary collaboration and the development of advanced theoretical models and observational techniques. The potential loss of Polaris as a vital reference point in the night sky presents significant concerns for astronomical endeavors. Ground-based telescopes and celestial measurements would require recalibration, affecting the accuracy of astronomical assessments. The absence of Polaris could also impact navigation systems and cultural practices reliant on celestial landmarks, highlighting the significance of this cosmic event. The enigmatic behavior exhibited by Polaris underscores the need for deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding its irregular pulsations and provide definitive answers, recognizing the importance of advancing our understanding of cosmic intricacies. Ultimately, the answer to Polaris' fate remains uncertain, and only time will reveal its true nature. Nonetheless, the pursuit of knowledge and understanding in the face of cosmic uncertainty is a testament to humanity's enduring curiosity in unraveling the mysteries of the universe. As astronomers continue to monitor Polaris, the star's peculiar behavior prompts a broader evaluation of similar stellar phenomena. The study of other Cepheid variable stars, particularly those showing signs of irregular pulsations or unusual dimming and brightening cycles, is crucial. By analyzing these stars, scientists can gain insights into the mechanisms driving such anomalies and their potential consequences. Observations of these stars can help refine models of stellar evolution and provide more accurate predictions about the life cycles of stars like Polaris. Moreover, advancements in technology and observational techniques play a critical role in these investigations. The development of more sensitive telescopes and space-based observatories allows for more precise measurements of stellar brightness and pulsation patterns. This technological progress enables astronomers to detect subtle changes in stars that were previously imperceptible, leading to a better understanding of their behavior and potential fate. Another aspect under investigation is the role of interstellar environments in shaping the behavior of stars nearing the end of their life cycles. The interaction between a star's ejected material and the surrounding interstellar medium can influence its observed properties. Studying these interactions helps scientists understand how a star's environment could affect its evolution and eventual transition into a white dwarf or supernova. Furthermore, the impact of a potential Polaris explosion on other celestial bodies and cosmic phenomena is a topic of interest. The shock waves and material ejected from such an event could influence nearby stars, planetary systems, and even the formation of new celestial objects. Understanding these potential impacts provides a more comprehensive view of the cosmic processes at play and highlights the interconnectedness of various astronomical events. The scientific community remains committed to unraveling the mysteries surrounding Polaris and other stellar phenomena. Collaborative efforts across institutions and disciplines are essential for advancing our knowledge of the universe. The quest for answers about Polaris' fate and the broader implications of its behavior underscores the importance of ongoing research and the mission to understand the dynamic and ever-changing cosmos. In addition to studying individual stars like Polaris, researchers are also focused on improving theoretical models that describe the life cycles of massive and variable stars. These models incorporate data from a range of observational sources, including ground-based telescopes, space observatories, and laboratory simulations of stellar conditions. The integration of diverse datasets refines our understanding of the processes governing stellar evolution, including the complex interactions within binary and multiple star systems. Astrophysicists are also exploring how stellar explosions could influence cosmic phenomena, such as galaxy formation and the distribution of heavy elements throughout the universe. supernovae, including those from stars like Polaris, play a critical role in enriching the interstellar medium with elements essential for the formation of planets and life. By studying these events, scientists aim to gain insights into the life cycle of galaxies and the chemical enrichment of the cosmos.